This video is on the objective determine the critical value or critical values if it's a two-tailed test for a hypothesis test for the mean of the differences for the paired data. Right, and this is in order to define rejection regions. Right? Once you have those critical values, right, you'll be able to determine the rejection regions. Alright, and this is the second video on this objective, so hopefully you watched the first one. I'll probably explain a little less in this. Okay, so let's just take a look at the problem. Alright, so again, if you're unfamiliar with the topic, want to see more about it, click on More Instruction and look at their videos, their notes, their examples, and hopefully those help. Alright, so here a physician wants to determine if a supplement is effective in helping men lose weight. She takes a random sample of overweight men and records their weights before the trial. She then prescribes the supplement and instructs them to take it for 4 weeks while making no other lifestyle changes. After the 4-week period, she records the weights of the men again. Suppose the data were collected for a random sample of 6 men. So you're going to have 6 pairs of data, right, with their weight before the supplement use and then their weight after the supplement use, where each difference is calculated by subtracting the weight before the trial from the weight after the trial. So they're taking the weight after minus the weight before. And we're assuming that the weights are normally distributed, right? So that way it doesn't matter that the sample size is so small. We'll still be able to apply the theorem and use the student's t-distribution with 5 degrees of freedom, right? Because there will be 6 differences here. There are 6 pairs. First, they're asking what type of test is this? Is it a right-tailed test, a left-tailed test, or a two-tailed test? All right. So let's go to the paper here and I'll talk about what's going on. All right. So we have the man 1, man 2, and all the way down to man 6. They said she only took 6 men. Then we have, the first sample. The first sample of data is their weight before, right? Their before weights. So say B1, B2, down to B6. And then a second sample of data, 4 weeks later, with their after weight. And I'll call this A1 for after, A2 to A6. Now again, this is paired data. These are dependent samples. I can't just move data around here. These have to be the way they are. These two have to be in this row next to each other because they're related to the first guy. These two have to be next to each other because they're related to the second guy, and so on. So these are these have a relationship, a dependence. They are paired. Alright, so remember what we've been doing with these paired data is taking differences. Right, I take the differences in these data. Now they told us here, now I'm going to call this D for difference. And they're taking the after weight, the weight after the program minus the weight before the program, right? So we have, D1 would be A1 minus B1, right, after minus before, and then D2 would be A2 minus B2, and so on. And I'd have 6 of these differences, right? And then we're going to focus on this sample of 6 differences, right? And it has a sample mean. The mean of the sample would be called, D bar. It has a sample standard deviation, which would be called S sub D. Right? But if you were to do this, if this researcher were to do this for all possible groups of 6 men, and look at these, differences in the D bars. Look at the D bar for all possible groups of 6 men. The distribution of the D bars would be a student's t-distribution with 5 degrees of freedom, because n equals 6 here. There are 6 values in this one sample of differences, and when you're doing a t-test with one sample, right, the number of degrees of freedom is the sample size minus 1. Right, so I'll keep that in mind, that we have 5 degrees of freedom. But this is neither here nor there. Let's get into the setting up the hypotheses. So first I want to talk about what this means. All the hypotheses related to these paired data sets and these differences, all the hypotheses are going to be related to this value called mu sub d that you're going to see. And this is the population mean difference in their before and after weights. All right, so this is for all men, not just these 6 men. Right? The population mean difference in weight. That's an E. Okay. So again, if I'm taking after minus before, this is if I were to do this for every man, all men, or all overweight men. Maybe the population's overweight men. But if I were to take every man from the population that's being studied, look at their before weight, give them the supplement, look at the after weight after 4 weeks, and then take their differences. And what would be the average of all those differences? That's what this mu d is. Alright, so then there's going to be a claim or some belief or some statement being tested related to this mu d. Now the physician wants to determine if this supplement is effective in helping men lose weight. So if you think of how the differences are taken, if they lost weight, that means their after weight would be smaller than the before weight. And if you take one number and subtract a larger number from it, it's going to be negative. So the claim here is that mu d is less than 0, is negative. All right, this would mean that the supplement helped men lose weight. Men lost weight or lose weight on average. All right. So that's the claim being tested. What this research is trying to determine. And then once a claim is established, you set up your hypotheses. Now this does not involve equality, as most of our claims haven't. So that'll be represented by the alternative hypothesis that mu d is less than 0, right? That this supplement actually helps lose weight, right? And then the null hypothesis would be the opposite statement, which would be that mu d is greater than or equal to 0. But as you've seen, usually they're just writing the equal part, because what we're going to be assuming when we run the test, we're going to be assuming the equality, that mu d equals 0. And if mu d equals 0, if the average difference in weight for all men is equal to 0, that means that this supplement didn't have any effect at all. Right? No weight loss on average is what this statement is, using this supplement. Okay, so you'd be assuming this, testing this, right? But you assume that there's no weight loss on average, and then through the sample and look at the sample differences and calculate your test statistic, compare it to a critical value. You would decide whether or not you like this. Do I like this assumption? Am I going to keep it or not? Am I going to reject it, get rid of it, or fail to reject it and keep it? And then after you decide that, then you'll talk about a conclusion, right? Make a conclusion about, do you support, does the evidence in my sample support the claim or not? Okay, but then, what we're asked though is what kind of a test is this? And that all comes from how the alternative hypothesis looks. And look, this is some parameter is less than 0, less than a value. So this is a left-tailed test. All right, hopefully that all looks familiar. How the alternative hypothesis looks tells you what kind of a test you're running. So when I set up a rejection region later under this student's t-distribution with 5 degrees of freedom, it's just going to be on the left side, right? A left tail rejection region. All right, so the first part, left tail test, because mu d is less than 0 is the alternative. That's that first option there. Okay, wonderful, cool, and read your answer explanations, please, just to make sure you know what's going on. Then there's a second part, because this is about determining critical values. What would the critical value be? Because again, it's only a one-tailed test, left tail, so there's only going to be one critical value. And because it's a left-tailed, it'll be a negative critical value in this case. Right? So again, I'll draw a picture. Right, so like I said, the distribution of my d bars in this case will be a student's t distribution with 5 degrees of freedom. So I'm going to draw that. Right, here's a number line representing t-scores, a symmetrical bell-shaped distribution above that. The t-score under the peak is a t-score of 0, and we're setting up this rejection region, and it's got to be in the left tail. So let's say this is the rejection region, and the rejection region, right, should have an area of alpha. Now they told us here that alpha was 5%, right? Alpha was 0.05. So this t-score I'm looking for, and using the symmetry, I'm looking for that. What's the t-score with 5% above it? Right? That's what this t with a subscript of 0.05 means. What's the t-score with 5% above it? And then we're taking the opposite of this to get the t-score with 5% below it. All right, so back here on the table, we have 5 degrees of freedom, so I'm in this first row. And we're looking for that t-score with 5% above it, and then we're going to take the opposite of that. So again, up here, the 0.05. So the t-score I'm looking for is 2.015. 2.015. So back on my piece of paper, this value with 5% below it in the left tail is negative 2.015. Right? There's the critical value of my test. And then, I would once I've calculated the test statistic, I figure out, is that test statistic in this region? Is it to the left of negative 2.015, or is it not in the region? And then I would reject the null hypothesis or not reject it based on that, and then make a conclusion. But all they're asking us for here is what would be the critical value. And again, be careful, it's a left tail. This got to be negative. Put in the negative sign, 2.015. All right, wonderful. I just completed it here. You might not. You might have to do some more questions, but hopefully, watching me go through this and looking at the more instruction when you need to, reading the answer explanations when they come up. Hopefully, all this stuff is helping you out when you go through this material on your own. And thank you very much for watching.